Our star, the Sun, has this incredibly long and complex magnetic past. But for most of that history, we've pretty much been flying blind, unable to see the whole picture. So the big question is, how did scientists manage to reconstruct a detailed history they could never actually see? It's a pretty amazing story of scientific detective work. I mean, think about it. It's a huge challenge. If you want to understand how the sun behaves over the long haul, and maybe even predict its future, you've got to be able to look back in time, way back, before we had any of the modern satellites or telescopes to map its magnetic fields. So how on earth do they pull it off? Okay, so let's dive into the heart of the problem here. We're talking about a massive gap in our knowledge, because for centuries, we just didn't have the tools to see what the sun's magnetism was really doing. Take a look at this timeline. We've been officially counting solar cycles since way back in 1755. But it wasn't until the 1970s that we could really start mapping the sun's entire magnetic field. That leaves almost 200 years of solar history in a period we can only call the Great Unknown. That's a huge blind spot. And look, this isn't just some dusty old academic puzzle. This missing history is a critical problem. It holds the keys to building way better long-term space weather forecasts. The kind that protect our satellites and our power grids. It also helps us figure out how the sun's energy output might influence Earth's climate over decades and centuries. Bottom line, we need this data to predict what our star is going to do next. So to crack this 200-year-old mystery, scientists had to start with the one piece of data they actually had. And it was a single, surprisingly simple clue from history. Yep, that's it. For this entire period, the one and only consistent, reliable piece of information we have is the number of sunspots, which dedicated astronomers have been counting day in and day out since the very first solar cycle. But here's the catch. Just knowing the number of sunspots isn't nearly enough. To actually build a magnetic map, you need the whole shebang for every single active region. Its location, its size, how much magnetic energy it's packing, and this really crucial property called its tilt. They had a single number, but they needed a full dossier. So, how do you turn a simple count into a complete dynamic map of the sun? Well, the answer is pretty brilliant. You build a virtual star, and you power it with two incredibly powerful computer models working together. Honestly, the best way to think about it is like a super sophisticated video game. The first model, SAGR, is basically the character generator. It takes that historical sunspot number and creates a whole cast of realistic virtual sunspots. Then the second model, AFT, acts as the physics engine, simulating the world these sunspots live in and tracking how they move and change over time. So let's look closer at SARG, the synthetic active region generator. What's so brilliant about it is just how simple its input is. All it needs is that historical sunspot number. From there, it just randomly samples from everything we know about sunspot statistics, like their typical sizes and latitudes, to create a complete and totally plausible list of virtual active regions. Okay, so once SARG has created our cast of characters, the Advective Flux Transport model, or AFT, takes the stage. This is the real physics engine. It's like a time machine for magnetism. It solves all the complex equations that describe how magnetic fields get stretched, twisted, and dragged across the sun by these massive plasma flows, basically playing out 265 years of magnetic drama. All right, so simulating 265 years is one thing, but making sure it doesn't go completely off the rails, that's another thing entirely. And this is where things get really, really clever. Right? I mean, this was the biggest hurdle they faced. When your simulation runs for more than 2 centuries, even the tiniest errors at the start can compound and snowball until your final result is totally disconnected from reality. So how do you keep it on track? And the answer, amazingly, lies in this subtle but super critical property of sunspots. See, sunspots usually show up in pairs with opposite magnetic polarity, kind of like a little bar magnet sitting on the sun's surface. The key is the tilt of that pair compared to the sun's equator. So here's the trick, and it is so smart. At the end of each simulated 11-year cycle, the model looks at the magnetic field up at the sun's poles, and based on what it sees, it makes a tiny, systematic adjustment to the average tilts of all the virtual sunspots that are going to pop up in the next cycle. Now, why would they do that? It's because the strength of the polar fields at the end of one cycle is the absolute best predictor we have for the strength of the next one. So this whole tuning process, it's like having these little guide rails that gently nudge the simulation back on track every 11 years, making sure the entire 265-year history stays physically consistent. Okay, so after all of that, after generating millions of virtual sunspots, running them through this powerful physics engine, and carefully tuning them over 24 solar cycles, what do you actually get at the end? Well, you get this. And wow, this is the result. A continuous 265-year map of the sun's magnetic history, all the way from 1755 to 2020. You can totally see why they call it a magnetic butterfly diagram, right? The patterns that the sunspots make over each cycle look just like a butterfly's wings. The truly mind-blowing part is that this whole reconstruction, which, remember, started from just a single number, it perfectly nails all the classic features we know the solar cycle has from modern observations. You can see the butterfly wings, the correct magnetic polarities, even the fact that stronger cycles have sunspots that show up at higher latitudes. It's just a massive validation of the whole approach. Okay, but let's be real, it's a gorgeous picture, for sure. But the million-dollar question is it right? How can we actually be confident that this synthetic history is what really happened? Well, the cool thing is we can check it. For the recent past, from 1996 to 2020, where we do have direct satellite observations, we can put the simulation right next to reality. And as you can see, just look at that. The agreement is stunning. The big patterns, the timing, it's an incredible match. And this isn't just an eyeball test. They put a number on it. When they compared their simulation to other historical records, the statistical agreement, it's called a Pearson correlation, was over 0.85. Now, in statistics, a perfect one-to-one match is a 1.0. So getting over 0.85, that's ridiculously good. It gives us huge confidence that this thing is the real deal. It's really like the researchers said themselves. This work gives us a physically consistent and data-constrained view of our star's magnetic life story. Basically, we now have a window into the sun's past that we never, ever thought we'd have. This achievement fundamentally changes the game for solar science. By being able to reliably look this far back in time, we can now test our theories about the sun over timescales we never could before. And it really leaves you with one massive question, right? Now that we can finally read the sun's past, what is it going to tell us about our future?